Hi, and welcome to Lecture 8. As promised, tonight we have Greg. Greg and I were co-lecturing this module for the last 4 years. We basically started this module about 5 years ago together. He was a senior lecturer here at City University, and about a year and a half, roughly about that time, he left City University, and he's a chief computer scientist at Huawei. And he had a talk about 10 days ago about deep learning applications in computer vision, which is online if you want to watch it later. And he's one of the best, and I leave it to you.
Well, thank you. Hello, everyone. It's a real honor to be back at City. As Slabaugh said, we started this module many years ago, and it's great to see it's still going and a lot of people here. So I'm looking forward to a fun time tonight. At any time, if you have questions or have a comment, just feel free to interrupt. It's good to have some dialogue going back and forth. So today we're going to talk about 3D vision. So everything we've covered so far in this module has been about 2D images. Today we're going to add a third dimension and see where we get to. Okay, so just a quick recap from last week. Last time you learned about biologically inspired computer vision. And in fact, you learned about how the eye works and processes data, and that naturally led to the HMAX algorithm, which is a very nice approach for image classification understanding. Following on from that, you learned about deep learning, which is a very popular topic right now in computer vision. And basically in deep learning, you have sort of these different Legos, you can think of them. You've got things like convolution, max pooling, ReLU, fully connected layers, etc. You can put these together into an architecture, and then that architecture can be trained to solve a problem, like image classification or image super resolution. And to do that, you need to set up a loss function and then optimize it using, for example, stochastic gradient descent. Once you set that up, you can solve all sorts of cool problems. Last week you learned about object detection, which is really an interesting problem. And if you have temporal data, you can use recurrent models, which are good for modeling time series. Okay, so today we're going to talk about 3D, and 3D covers a lot of topics, but today we're going to cover the basics. We're going to talk about stereo vision. When you have 2 or more cameras that are photographing the scene, what can you do with that? So we're going to get into camera calibration. You'll understand how to project 3D points into a 2-dimensional image. And if you're able to do that, you can then do really cool things like augmented reality. And I'll show you how to do that. And in fact, in today's lab, there's a lab today, you can actually take 3D surfaces and project them into images. We'll also cover structure for motion, which allows you to reconstruct 3-dimensional shapes from video sequences, and we'll talk about point clouds as well. Okay, so as Slabaugh said, I've worked here at City for quite some time. I've also worked in industry. Back in the day, I worked for Siemens, the German company. We were doing all sorts of things, but working in 3D, actually designing hearing aids. So we took impressions of people's ears, then we pulled the impression out, and then we scanned it in 3-dimensionally. And then we did some 3D printing, and then we put electronic components into the hearing aid. So that's a nice application of 3D vision and 3D graphics. I've also done some other 3D work here at MedicSite. We were actually detecting precancerous lesions in the colon using 3D computer vision. And one of my PhD students did some joint estimation from video. So you have 2 cameras, you move your hand in front of the cameras, and it figures out where all of your joints are as you articulate your hand. So these are some kind of cool applications you can do with 3D and things that I've done. Okay, so if we're going to talk about 3D computer vision, here's a good definition. It is 3D computer vision can be described as extraction of 3D information from digital images. Okay, so that's very broad, and in fact, 3D vision covers loads of things. For example, here you might have a collection of images taken from different viewpoints, and you want to then reconstruct a 3-dimensional shape which projects back to the images, okay? If you can do that, then actually you can infer the three-dimensional geometry and the texture on the surface just from a collection of 2D images. Here's another example of, in this case, segmentation. Okay, so you learned about segmentation a few lectures ago. Here is segmentation again, now in the context of 3D. So we've got some MR image, and we're trying to segment a lesion. Of course, self-driving cars. Okay, here we have a LiDAR sensor, which is on a car. It's shooting out light in all of these different directions. You can reconstruct the point cloud and infer in 3D. And many other applications. Here's augmented reality. So you have a headset which allows you to see virtual content. And in order to integrate that well into the actual world, you need to track the head movement and project the object in a consistent way. Okay, so when we're talking about 3D, one of the most sort of basic concepts is stereo vision. And in this case, we have 2 or more views of the scene, and they're available from different viewpoints, okay? So a standard situation is you actually have 2 separate cameras. So I have a camera here, a camera there, and I can take pictures at the same time and then infer about the world in 3D. But another scenario is you actually just have a single camera, okay? And you've got maybe a video sequence you're recording, so as you move the camera, you can generate different views that way. So a very fundamental problem in stereo vision is to find correspondences. A correspondence is just a match. So you know a point in one image, you find its matching point in the other image, okay? And so since the 2 points match, we call them correspondences because they correspond to the same point. And if you can do that, then you can infer the relative distance of objects from the camera. So this relates to depth. Okay, so you know how far away the object is from you based on these correspondences that you find in multiple images. So in fact, the human's visual system achieves stereopsis as well. So we have binocular vision. Okay, so we all have 2 eyes. And for a human, typically the eyes are separated by 65 millimeters, depending on your anatomy. So you have 2 images of the world that are coming in, from your 2 eyes. And then your receptive fields are going to fuse those images to recognize the different positions. And then the amount of displacement the points, the corresponding points move, is called the disparity, okay? And disparity is related to depth. So I'd like to run an experiment. So what I'd like you to do is stick out your right hand, okay, and put your thumb up. And I'd like you to close one of your eyes, maybe your left eye, okay? And keep your thumb at arm's length and cover the red circle, okay? Once you've got that, then switch your eyes, okay? Hopefully you see that your thumb is moving a little bit left to right. Are you with me? So you kind of go from your left eye to your right eye. Now what I'd like you to do is move your thumb closer to your face, okay? Do the same thing. So cover up the red dot, and then switch your eyes. What do you observe? Yeah, there's more shift, right, when the thumb is closer to your face, okay? So that shift is called disparity. So the disparity is increasing when the point is closer to your face or the camera. We're talking about computer vision. So in fact, we could say the disparity is inversely proportional to distance. So points that are far away have very little disparity. They don't move much at all. Points that are close to the camera are going to move a lot. And in fact, this is a very well-known effect. I'm sure many of you may have seen Avatar. This is a really big movie when it came out. But really all of these 3D movies, what they do is they have 2 views of the scene, and they're basically giving you different views, and they're coding them based on distance, okay? So things that are closer to the camera, say like this character, are going to have more disparity than things that are very far away. And that's how the brain is going to infer depth. And in fact, you see like his hand and his legs, there's a lot of disparity here. There's a lot of shift on the character, so we're rendering two different views into the two viewpoints. But points very far away, there's very little shift. Okay. Okay, so as a computer scientist, you might want to compute disparity if you're given two images. And this is a very classic problem in computer vision. So what we're going to need to do in this case is to find the correspondence. So for example, this is my image, my left image, okay? And my left image, I have a point X. And the task is to compute the point X prime, which corresponds to X. And they correspond because they relate to the same point in three-dimensional space. Okay, so if I go from the center projection in the left image through the pixel into 3D space, it's going to hit this object at this point, capital X. And if I forward project this point, capital X, into the right image, I'm going to get X prime. So these two points correspond because they relate to the same point in 3D. Okay, so what we want to do in this case is, given a point in one image, we want to find the corresponding point in the other image. So here in my left image, I have this point X, okay? This was a friend's desk. And at the corner of his telephone, I've got this point X. What I want to do is find point X prime in the right image. How do you think I might do that? How would you write an algorithm to find X prime? Any ideas?
Object detection, we saw before.
Say it again?
Object detection, like we saw before.
Object detection. Okay, that's a good idea. So you can build an object detector. So, for example, you could train a neural network or something to find these kind of corners, and then look for matching corners in the other image. That's a good idea. Any other suggestions? Yep.
Could you just take a sample of the pixels around it and
Uh-huh.
search for it in the next image?
Yeah, that's a great idea. That's called template matching. So what you're going to do in that idea is you grab a little patch of pixels around X, okay, and then you're going to search in the other image until you find a match. And that search can be based on the difference between the colors of the patches, and hopefully you get a nice peek right here at the true location. So those are all great ideas. There's something that's really interesting, though, when we talk about stereo, and that is that we can actually reduce this computation to one dimension. And to do that, we need something called epipolar geometry. So what's interesting here is that the point, capital X, it's in three-dimensional space. Okay, I don't know exactly where it is if I'm in the left image and I have this little point X. But I know the corresponding point, it's got to be on this line somewhere. And if I project that line into the other image, then I only need to search along this line instead of the entire 2D image to find the correspondence, okay? So what we can do then is try to find this line, L prime. This is called the epipolar line. And so instead of searching the whole image, I can reduce the computation and only search along this line instead. So I can then check all these points, and I can still do that same idea of either using an object detector or checking patches. They're both good ideas, and they still work, but now I only need to do it along one dimension. So you can imagine really reduce the amount of computation here. And it goes both ways. So if I have a point over here, maybe this x2, if I want to go find it in the other image, okay, it's the same deal. I have an epipolar line in the left image, okay, and I only need to search along that line in order to find the correspondence. So the nice thing about epipolar geometry is that it makes it more efficient to find these correspondences, and especially if you want to do this in real time or make it fast, these kind of efficiencies are really important. Do you have questions?
Explaining how the line is defined.
Yeah, so the line is defined based on these 3 points, actually. So you've got the center of projection in the left image, okay? You've got the center of projection in the right image, okay? And then this point, little x, if you shoot a ray out from the center projection of the left image through X, it's going to form this line out into 3D space. So you can imagine you can project all those points on that line into this plane, and you get a line.
How do you know what the center of projection is?
Oh, great question. So we're going to come to that. That relates to camera calibration. So we are assuming at this point that we know the center of projection, and we know this point X in the image. Now, in general, you might not know, so there's a separate exercise to calibrate your camera to figure out where these points are in 3D space, but also other things, like you learned about the intrinsic camera matrix back in lecture 2, I believe. All of those, all those points that are in the intrinsic camera matrix, like the focal length, the skew, the center of projection, all that, it's going to also be computed in a camera calibration. So I'll cover that later in today's lecture. Okay, so here's an example of doing epipolar geometry, and this is using the MATLAB toolbox. So basically, what you're seeing here is I might have a point, say this point on the corner of this monitor. What I can do is use the epipolar geometry and figure out what line it's on in the other image. And that's encoded here on this yellow line. And so if I need to go look for this point, all I need to do is search along this line to find the match. And it's the same thing with all these other points. Any questions with that? Okay, so basically epipolar geometry is going to allow us to constrain the search to the line. And there's some terminology you might hear when you're talking about epipolar geometry. So the two centers of projection coupled with the point in 3D, these form a plane, okay? We've got 3 points in 3D space. That forms a plane. That plane is called the epipolar plane. Another term you might hear in stereo vision is baseline. Baseline is the distance between the two camera centers, okay? So it's this, the length of this dotted line between the purple points. And then we have epipoles. Epipoles are these little points E and E prime, which explain where the center of projection projects into the other plane. Okay, so my point C in the left image is projecting to this point E prime in my right image. And likewise, C prime is projecting E in the left image. So what's interesting about the epipoles is that every epipolar line goes through the epipole. So here, for example, I have an epipolar line in my right image, and that line has to go through the epipole, E prime. So hopefully you can appreciate there's some geometric constraints involved in stereo vision when you have two views. So if your images are uncalibrated, okay, you don't know any of these calibration parameters, then what you can do is compute something known as the fundamental matrix. And we're going to denote that with the symbol F. So F is a 3x3 matrix, and it really encodes the epipolar geometry into an algebraic representation. So here, it makes it actually really easy to compute an epipolar line. If you know the fundamental matrix F, okay, you can just take that point X, multiply it times the fundamental matrix, and then that gives you the equation of the line. So it's super easy if you know the fundamental matrix to get the epipolar line. And there's another constraint. If X prime is on the epipolar line, then this construction, X prime transpose Fx is 0. Okay. So the fundamental matrix, it's got a lot of properties and it's super interesting. If you'd like to know more, I'd recommend checking out this book. It's called Multiple View Geometry. It's by Hartley and Zisserman, and they wrote a very detailed book about how to sort of understand the geometry of multiple views. Another couple points about the fundamental matrix, if you have F going from 1 to 2, then if you want to go the other way from image 2 to 1, you just take the transpose, and so on. So, so if you want to figure out this epipolar geometry and simplify your computation for correspondence, you need the fundamental matrix. But then how do you get the fundamental matrix? So there are a lot of ways actually to estimate the fundamental matrix. The best known approach is called the 8-point algorithm. And essentially it encodes that equation I had before, x prime transpose fx equals 0, okay? So you can just put that out and sort of write it out in an algebraic way, okay? And what you get is kind of this long expression, okay? But if you look at it, it's linear in all of these terms, f11, f12, f13, etc. These are the terms that are in the fundamental matrix, okay? So every correspondence you have gives you one of these equations, okay? So if I know, if I know one point in an image and I know its correspondence in the other image, okay, I have x and x prime. So then I can feed all of those values in here. And then what's left is just to estimate these parameters f from linear equation. Okay, but the thing is there are 9 of these parameters in the matrix, okay? So if you want to be precise, you need to have at least 9 correspondences in order to estimate the fundamental matrix, right? Actually, you can set the determinant of the matrix to 1, so actually reduce that to 8 correspondences. Now, if you have loads and loads of correspondences, it's not a problem to put them in this formulation, okay? So here's my first correspondence, here's my second correspondence, and so on until I have n correspondences. And it could be 20 or 100, that's fine. And then you can solve a least squares equation to estimate these parameters f. And this is super easy in MATLAB. You can do that in just like one line of code. Okay, so you can write your own code to estimate the fundamental matrix, but unsurprisingly in MATLAB there is a function to do it for you. It's called estimate fundamental matrix. So super easy. What you're going to do here is you're going to feed it a bunch of points, okay, M1, and then they're matching points M2. And these are the correspondences. So maybe I have this point, this green point here, it's the corner of the monitor. If I have the correspondence in the other image, then I've got 1 correspondence. If I have 8 of these correspondences, I can feed them into this function. And here you go, here's some code which does that. And then I can call this estimate fundamental matrix function. And here I'm using this normalized 8-point method. Okay, so this is the 8-point correspondence technique I just described. And out pops out the fundamental matrix. Okay. So if you have your correspondences, you can get the fundamental matrix in essentially one line of code. Okay, so once we have the fundamental matrix, now we can compute epipolar lines, we can compute all of these epipolar constraints. And here's an example of doing that in code. Okay, so I've got my fundamental matrix, it's this 3x3 matrix. And what I'm doing here is I'm taking my first point in my image, okay? And in this case, it's the top left point of this book, okay? And then I'm going to just multiply the fundamental matrix times the point. And here I'm adding 1 to make it homogeneous, okay? And then I get an equation of a line. And then if I just draw that line, okay, that's what this code is doing, here's what it looks like. So I've got this blue line, and sure enough, it's going right through the corner of that book. So the correspondence indeed lies on the epipolar line. Does it make sense? Yeah?
How did you determine the correspondence initially? Was it just manually, or are you doing some basic object detection?
This was done manually. So you've got a really good question here. I've got, in a couple slides, I'm going to describe how you do it automatically. But right here, it's manual. So I literally found all of these points, clicked on them in Irfan view or whatever it was, got all these points myself, and then I fed it into that equation, or that function. But yeah, there are more automatic ways to do that, and I'll cover that in just a few minutes. Okay, any additional questions? Okay, so not surprisingly, MATLAB also has a function to compute your epipolar line. So here you can just pass in the fundamental matrix F, and then the point in, say, the left image. This will give you the epipolar line. And if you want to, you can even visualize that using, you know, this line function, and you can clip the line to the border of your image. So if you do that, it looks like this. So here, of course, the epipole is right here, because all of the epipolar lines are going to go through the epipole. Okay, so back to the question that was just asked, which was an excellent question. You know, how do you get the points to compute the fundamental matrix? Well, it's interesting because there's kind of a chicken and egg problem here. If you want to find correspondences, knowing the fundamental matrix is really helpful because you can reduce the search to one line, right? But in order to get the fundamental matrix in the first place, we need to have correspondences. So kind of got an issue here. The other thing is that we want to make this as automatic as possible, ideally 100% automated. So you just feed 2 images into MATLAB, and you know, you've got all these correspondences, you get a fundamental matrix, you can do all sorts of stuff. So how can we do this? Well, there's a really cool technique called ransack, which is super useful in this problem. So if you haven't heard it before, ransack stands for Random Sample Consensus. And although it's used a lot in computer vision, I think of it more as a data science type algorithm, okay? What it allows you to do is to estimate a model when there's a lot of noise and outliers in the data, okay? And that happens all the time in your life. So ransack is a really general purpose and useful algorithm. So essentially it's like a hypothesize and test methodology. So the first thing we're going to do is we're going to randomly subsample a set of correspondences, and I'm going to call that C. Okay, so I've got a bunch of points in one image, I've got another set of points in the second image. I don't really know which points correspond. Okay, but I'm going to randomly subset a sample, and you know, I'm going to pick 8, and I'm going to call that C prime. Since I have 8 correspondences, I can then estimate the fundamental matrix using the equation, the function I described earlier. So now I've got my fundamental matrix, but the thing is, my fundamental matrix, it might not be that good because maybe my correspondences aren't really corresponding. Maybe some of them correspond, but maybe some of them don't. So I might have outliers in my data. But that's okay, I can still estimate the matrix even though it might not be the best matrix. Then what I can do is I can score this matrix by determining the fraction of inliers in the full set of correspondences match the model. Okay? So I just kind of grab some correspondences, I compute my fundamental matrix, and then I want to score that matrix. Is it good? Is it bad? I compute the number of inliers, the number of correspondences that match the model. And if that's high, then I can infer that my fundamental matrix is good. If not, I can just go back and I can sample another set of correspondences and I can iterate you know, a certain number of times until I get the best fundamental matrix. So let me give you an example. In this case, I'm going to show you an example for line fitting, which is maybe simpler to visualize and put into PowerPoint slides. But it's the same idea if you're doing a fundamental matrix or you know, some other sort of mathematical model. So in this case, what we're going to do is try to fit a line to these points. Okay? Now if you look at these points, they're pretty noisy. And there's probably, it's not totally obvious what line should fit through these points. Okay, so if I'm going to use ransack for this problem, the first thing I'm going to do is randomly subsample the feature points to form a model. My model in this case is a line. Okay, so how many points do I need to estimate a line? 2, right? So I'm just going to grab 2 points. Okay, they're denoted with a purple color here, and then I'm going to fit my line. Okay, that's super easy to do. And now what I want to do is score my line. Is this a good line? Is it a bad line? In this case, the line's not great because the rest of the data doesn't really support it. Here I have, within some margin of error, I have an additional 4 points denoted in green here, which I can consider inliers, so they match my model. Okay, so these points are consistent with the line I just estimated, but the other points are not consistent. So this isn't a bad line, but it's not necessarily a good one. So can we do better? Well, let's just go back and do it again. So you can imagine you can do that maybe 100 times, maybe 1,000 times, until you find a line that has a lot of support from the data. And in this case, I sampled these 2 purple circles, okay? I got a line where many of the other circles agree with me. So here I've got 12 inliers, where before I only had 4 inliers. So this is a very classic approach to estimating a model when you have outliers in the data. Does that make sense? So this is how you can use ransack to fit a line. You can also use it to fit circles and so on. There is a lab today, and if you do the lab, you'll actually get to fit circles using ransack. But back to our problem, okay, our real problem here is to, oh, sorry, go ahead.
Just a quick question. How do you decide how much margin you're going to take?
Yeah, that's
Capture the inline.
right. That's a good question. So that's like a hyperparameter. So you have to decide, what your threshold is. We also have to decide how you're going to, how much times you're going to loop, for example. Imagine doing this 100 times, 1,000 times. So in some sort of practical context, you're going to want to limit the number of iterations you do.
There's no, you're not moving in any direction, though. You're not trying to move in the direction of randomly.
That's right. So there's no like gradient
Just-
descent here or anything
right.
like that. It's just random. This is like a stochastic optimization algorithm. So you just randomly pick 2 points
And then you stick with the best one.
Yeah,
until,
that's right.
Until that gets better.
That's right. So, I mean, you can imagine a variant of ransack where maybe you start off with 2 points, and then you do some sort of gradient descent until you find a local optimum, and then maybe you iterate again. And so, you can imagine there are other variants of ransack. And in fact, if you look in the literature, there's quite a bit of literature on different twists we can take on this technique. Okay. So back to our problem of estimating the fundamental matrix. So now we have this tool, ransack, where we can deal with outliers and estimate a model. So we want to apply it to this problem. So what we're going to do is first we're going to find features in both of these images. Okay? And by features I mean points. And good points, you've learned a lot about good features. You could use, for example, surf. Okay? So you can use surf to find very distinctive points in both images and then try to find some correspondences. Okay, so here I'm detecting some surf features, okay, and then extracting those features. And here what I'm doing is I'm trying to match those features, okay. Now these matches, they might be right, but they might also have outliers, okay, which are incorrect matches. But that's okay. I've got a technique that can deal with outliers. And so I'm going to call this estimate fundamental matrix function. And here I'm going to tell it to use ransack. Okay? So essentially what I'm saying is, look, I've got these points. I think they correspond, but not totally positive. Use ransack and give me the best fundamental matrix you can, given these parameters. So once you've got that, then you can take the fundamental matrix, and you can then compute the epipolar line. You can visualize things, and here again I've got a point. This point in this blue square here is the line going right through there. So this is how you can use MATLAB to use the fundamental matrix and compute it using ransack. Okay, any questions with that? Okay, so we talked about how the fundamental matrix is really helpful for reducing the amount of computation, so you can search on a single line and find correspondence. And that's great, but sometimes that's a little inconvenient because you know, I can go find this epipolar line in this image, but it's on kind of a weird angle, okay? So in rectification, what you do is you actually adjust the image, warp it, so that you can reduce the search not only to a line, but a line that's axis aligned, okay? So here I've got a horizontal line, okay, in both of these images. And essentially it's an image warping, okay? And now if I want to find, say, the correspondence of x in the right image, I can just search along the horizontal line. So you can imagine how that might even be more efficient. You know, in code, you just have to go, you know, along a horizontal scan line. So again, this is a type of image transformation or warping, which will, you know, make the computation simpler. In MATLAB, there's this function called estimate uncalibrated rectification, which you can use to do this type of effect. Okay, so once you're able to you know, use the fundamental matrix and reduce the search to a line, you can even rectify your images. Really, where we started this lecture, we were trying to find disparity. Okay, so we talked about disparity being large for points close to the camera and small for points far away, and it's related to depth. So in order to you know, get the disparity, what we're going to need to do is find dense correspondences. So every point in the left image, I want to find its match in the right image. Okay. So to do that, standard algorithm is kind of like this, where you start off with a point in the left image. You know the epipolar line, and it might be it's rectified. That line is horizontal. Then what you're going to do is you're going to step along this line, and you're going to compare the pixels to look for a match. And typically you do use a patch around the pixel, so it's not the pixel itself, which might be a bit ambiguous. You form a patch around the pixel, and you compare patches. So here, for example, I've got a patch in the left image. Okay, I'm calling that P. And in the right image, I'm going to extract all these patches along the horizontal epipolar line. And I can compute some measure describing how well these patches match. And there are loads of different measures. I'll cover those on the next slide. But the idea here is to find the patch that optimally matches the one on the left side. Okay. So as I move this, as I move along the epipolar line, okay, I can compute this matching cost, and hopefully at some point it reaches a minimum, and that minimum matches the true location in the other image. Okay. So this is how I can find dense correspondences. For every single pixel in the left image, I basically repeat this algorithm, and I can find a matching point in the right image. Does that make sense? Yeah?
What makes correspondence dense?
What I mean by dense is we're going to do it for every single pixel. But, yeah, so for every single pixel in the left image, I'm going to go find a match in the right. Okay, so there are loads of different ways to compare these patches, and in computer vision textbooks, you'll see all sorts of similarity metrics or matching costs that are used. Some of the standard ones include the sum of squared differences, okay? And here, essentially, what you're doing is you're just going over your patch, okay? Your patch is denoted by x and y, so x is horizontal, y is vertical. And for every pixel in the patch, you're just going to compare it to the matching pixel in the other patch. And here, D is the disparity, okay? So it's telling me how far along I've moved along the epipolar line. So I'm just going to search along that epipolar line until I find a patch that minimizes the sum of square differences. In that case, the patches, you know, have very similar colors. A different approach is to use the sum of absolute differences, Okay, and this is pretty similar, except we're using an absolute value. There's also the normalized cross correlation. You might see this in a textbook as well. A little more complicated, but essentially you're subtracting the mean from your left patch and dividing by the standard deviation, and then same thing with the right patch. So you're subtracting out its mean and dividing by its standard deviation. So it's a bit normalized. So these are different ways in which you can compute if the patches match or not. Okay, so believe it or not, in MATLAB there is a function which basically does all this stuff for you. It's called disparity. And essentially it can compute disparity for you given two grayscale rectified images. Okay, so you've got to rectify the image first, and then it's going to search for correspondences along these horizontal lines. So this function uses the sum of absolute differences as the matching cost. And as a programmer, it's up to you if you can configure the size of the patches by setting this block size parameter. Its default is 15. And they've got different sort of hyperparameters that you can use on this function. You can kind of play around with it if you want, like block matching or other approaches. And here's an example. So I'm going to load two images. Okay, I've got the left image and the right image. Here is one of those images. Okay, and here I'm going to basically compute the disparity using this disparity function. Okay, and then once I have this disparity map, then I can visualize it. And here, points that are closer to the camera are given a kind of hotter color, so like yellow, for example, and points that are farther away from the camera are given this kind of colder color, in this case kind of a cyan. So you can see here, actually we've got a pretty good representation of the depth of the scene, okay? Because here we've got the chairs, the objects that are closer to the camera, they pop out compared to objects further away. So you can see the disparity that we're computing. It's definitely related to depth. And if you use block matching, actually it works okay, but there are some holes here. So there are some errors. These blue regions are actually estimated incorrectly. So it's not super precise in that case, but not bad. And I've got a video here, but unfortunately I'm not connected to the internet. So maybe you can check this out later on your own. But essentially it's a video showing real-time stereo. So there's this company, they've got a camera, in fact it's got two cameras on it, and it's able to process the data so fast that they're able to do it on a video feed. So as you move this camera around in three-dimensional space, it's reconstructing this depth map, and you can see objects closer to the camera versus far away. Okay, and it's all live in real time. So this is really the state of the art at the moment. You can do this on a video feed, and it's pretty amazing. Okay, so we talked about disparity and how it's related to depth, but if you actually want depth, more work is required. But don't worry, it's not hard. We said before, depth is inversely proportional to disparity. Okay? So we had our thumbs. When it's close to your face or the camera, you get more shift than when it's far away. So if we want to upgrade the disparity to depth, really what we need to know are two things. We need to know the baseline, okay? That is describing how far away the two cameras are from each other. And for that, if you have a stereo rig, you buy it from the internet, maybe they'll tell you, how separated the cameras are, or you can just measure it yourself, like with a ruler. You also need to know the focal length as well. So we talked about the focal length back in lecture 2 in this module. If you want to get the focal length, the best way to do that is to calibrate your camera. So I'd like to talk about that next. Okay, so if we're thinking about camera calibration, what we want to think about are coordinate systems. So first up is world coordinates. And in world coordinates, what you've got is a single coordinate system. Okay, here's x, y, and z. And each object is going to have its unique location in space. So here I have this tree, for example. Maybe its position is 0, 10, 0. Okay, so 0 in x, 10 in y, and 0 in z. Here I have a cow. Okay, maybe the center of the cow is at this location, 10, 0, 0. And I might have a camera as well that's recording the scene. And that has a location in space as well. Okay? So in my world coordinate system, all of these objects have a unique location. There's also a camera coordinate system. And here it's kind of related to the world coordinate system, except here in the camera coordinate system, the origin is at the center of the camera. Okay? So here, the origin, it might be somewhere else, like some point through space. But in the camera coordinate system, the origin is at the camera, center of projection. Okay, so you've learned about the intrinsic matrix. There's also this thing called the extrinsic matrix. And the extrinsic matrix, it encodes the position of the camera in space as well as its orientation. Okay? And this is going to encapsulate the transformation from world coordinates into camera coordinates. So unsurprisingly, you can represent this using a matrix. Okay? And the matrix has a very specific form. So on the left side of the matrix, you've got some rotational components. Okay, this is like a 3x3 matrix. And on this fourth column, there's the translation components. Okay. So the rotation matrix, it has actually 3 degrees of freedom for rotation because you can rotate around 3 different axes. Okay. And so you can represent that actually as a composite matrix. Here I'm going to rotate around the z-axis first, then the y-axis, and then finally the x-axis. Okay? And you'll see there's only one angle in each of these matrices. So I actually have 3 degrees of freedom representing the 3 rotational components of the transformation. And then I also have these 3 components for translation, which basically tell me where the camera is in space. Okay, why don't we take a break here for 10 minutes, and when we get back, we'll tell you more about the extrinsic matrix, and we'll get into augmented reality. Okay, yeah. Oh, hey. Me too. I'm going to borrow some of that. Yeah, I'm going to go into more detail. Yeah, that was very good. Okay.
I mean, I'm still trying to see one because I wanted to go one and just 2. I just was wondering because all of this last year's goals
Not surprised. Okay, so before the break, we were talking about the extrinsic camera matrix. You've already learned about the intrinsic camera matrix. Here, the extrinsic is encoding the rotation and translation parameters of the camera. So if you have a camera, you're going to move it around in the scene. Okay, the translation's changing. If you rotate that camera, the rotation's changing. And it's encoded in this matrix. Okay, it's a 3x4 matrix where we have the left 3x3 submatrix is encoding the rotation, and then the right column is encoding the translation. Okay, so if you know all those parameters, like you know the angles theta, you know the translation components, then you can actually form your own extrinsic matrix. It's not hard. In fact, you can do the rotational part like this. Okay, so here on my previous slide, I showed you the equation for rotating around the x-axis, y-axis, and z-axis. So you could just write that code up very easily, okay? And then you can multiply those matrices together to form the rotation matrix. Okay, that's kind of what we saw here. Here's the equation form. Here's the code form. Okay, so you can do that, and it's actually pretty easy. Now, something to be aware of in the extrinsic matrix, the translation component, it's not the position of the camera C. Instead, it's the position of the world coordinate origin in camera coordinates, which basically means you take the camera location and then you multiply it by the rotation matrix, where the rotation matrix is given here. Okay. So if you want to, you can check out this link. It's really cool. Somebody made a WebGL page where they've got these Java applets, and you can kind of play around with the extrinsic matrix and see what happens as you start manipulating the parameters that are in the matrix itself, like the rotation components and the translation components. Okay, so anyways, if you want to project from 3D to 2D, you've got to use the intrinsic matrix as well as the extrinsic matrix. Okay, so we're going to put these things together to do the projection. So this is how it works. What we're going to have is a point in three-dimensional space. Okay, so it's got an x, y, and z component, and I'm going to make that homogeneous as well. So I'm going to add a 1 here. Okay, so here's my point in three-dimensional space. I'm calling that capital P in this slide. Then what I'm going to do is I'm going to multiply it. Here's the extrinsic matrix. Okay, this is the matrix we were just looking at. It's got the rotational component on the left, and here's the translational component. So I'm going to multiply the point times the extrinsic matrix, and then I'm going to multiply that times the intrinsic matrix. Okay, and that's going to give me this point x, y, w. Okay, so essentially what I've done using these equations is I've taken a three-dimensional point and I've projected it to 2 dimensions. Are you with me? So then to get the actual pixel location, I'm going to divide by W. Okay, so I'm going to dehomogenize the homogeneous representation. And then I've got the actual pixel location in the two-dimensional image that this 3D point projects to. Does that make sense? So what I'd like to do actually is an exercise. So if you could pull out a piece of paper, we're going to do this by hand, just to make sure that you understand how it works, because this really is the fundamentals of projecting from 3D to 2D. So pull out a piece of paper. What I'd like you to do, actually, is project this point P, okay, 90, 90, 1, okay, X, Y, Z, here's the W component. What I'd like you to do is project it using the extrinsic matrix I'm showing you here and the intrinsic matrix. Be sure to be homogenized, and tell me where it projects to in the image itself. So I'll give you a few minutes to work that out. Feel free to talk to a friend, work it out together. It's all good. Need more time?
Oh, yeah.
Okay, let's work on this together, see if we can figure this out. So I think some of you are done, some of you are still working on it, but in the interest of time, let's see what we can do here. Okay, so we've got this point, okay, P, it's at 90, 91, and then here's the W component, so I made it homogeneous coordinate, right? Okay, so what I need to do is multiply P times the extrinsic matrix, okay? So my extrinsic matrix is up here. So I'm just going to put these things next to each other. It makes it a little bit easier to do the matrix multiplication. So here I've got 1, 0, 0, 10, okay? And then I've got 0, 1, 0, 10. And then I've got 0, 0, 0, 1. Oops, 0, 0, 1, 1. Right? Okay. So if we do this multiplication, what do we get? What goes here? 100, right? Okay, does everybody see that? So we've got 1 times 90, right? And then we're going to add that to 0 times 90, so that's 0. And we've got 0 times 1, that's also 0. And then we have 10 times 1, so that's 10. So I've got 90 plus 10 gives me 100. Okay, so that was right, whoever said that. Okay, what about the next one? 100? Yes? Kind of the same thing, okay, except this time it's 0 times 90, that gives me 0. But here I've got a 1 times 90, so I get 90 there and then 10, so that's 100. Okay, and what do I get in the last spot here? 2, right on, okay. So, you know, the 90 times zeros are just 0, and then I've got 1 plus 1 gives me 2. Okay, so what we've done here is we've taken this 3D point, this homogeneous 3D point, and then we've multiplied it with the extrinsic matrix, okay? So the next, now we're actually in camera coordinates. This is a point in world coordinates, this is a camera coordinates. Okay, we're not done yet though, because we also have to multiply by the intrinsic matrix. So let's give that one a go. So I'm just gonna put that down here. Again, makes it a little bit easier to do the maths. So here I've got 1, 0, 300, 0, 1, 200, and then 0, 0, 1. Okay. So what goes here? 700. Correct. So everybody see that? So I've got 1 times 100 plus 0 times 100, that's 0, plus 2 times 300. So I've got 600 plus 100 is 700. Okay, good job. What about the next one? What goes here? 500, right on. Okay, you're with me. So basically that's 100 times plus 400, right? And what's the last one? 2. Cool. Okay, so now what we've done is we've gone through the intrinsic matrix, okay? And now we're actually in 2D space on the image itself. How cool is that? The only thing is, this point, it's not dehomogenized, okay? So what we want to do is dehomogenize it so that the W component becomes 1. So that's really easy, okay? You're just going to divide everybody by 2. So what do I get? 350, 250, 1, okay? So here's my image, okay? Here I've got this point in 3D space, P. Got my center projection. This point, it's going to project to a point that is 350, 250. Okay. So that's how you can project from 3D to 2D, just by using some matrices, right? The way this works though is I know all of the numbers that go into the matrix. Any questions with that? Yeah.
Sorry, can you go over why you're able to again, you said you were able to divide it by 2.
Oh, yeah, sorry. So this is, yeah, so we've got a point here. This is a homogeneous representation of a point. So what I really want is a dehomogenized version. So what that means is I want this element to be a 1. And I can do that by just dividing everybody by 2. And that gives me 350, 251.
What if it is not
it being 2? What does it mean actually?
It doesn't really have an important meaning. So when it's 1, then we're in Euclidean coordinates. And this is what we're used to with image. So in this application, we want that to be 1. And so you're just going to divide by the 2 to dehomogenize. Yeah?
Could you possibly give a real world explanation of what the different bits are doing?
Yeah, okay, sure. So in kind of intuitive way, this is our point in 3-dimensional space, okay, that's P. And this next matrix is the extrinsic matrix, and essentially it's encoding the position of the camera in space as well as its orientation, okay? So if I want to project into the camera, I need to know which way the camera's facing, I need to know where it is, and so that's encoded by this matrix. So when I do this multiplication, now I'm in camera coordinates, okay? And then,
is that now, so we're in 2D space now?
well, it's still 3D. Well, yeah, okay, I guess it is 2D. Sorry. Yeah, it's 2D. It's based on the camera, though. So the camera has its own sort of coordinate system. Okay.
Yeah.
And you can think of it in 2D in the sense that we've got kind of an x and y axis, and then this axis represents depth. So earlier we were talking about depth, and actually, if you had a 3-dimensional coordinate, you could tell how far away the point is from the camera. But in this case, we're 2 dimensions. Now, in order to understand how to put that into the image itself, we need to understand what the focal length is, where so the focal length here is encoded with these parameters, and then this is telling us where the center of the image is. So by doing this, then we can actually project into the image, and we know precisely which pixel this point projects to. Does that make sense? Okay, cool. Okay, so so you can do that, okay? And now that you've done the mathematics on the page, you can imagine it's not too hard to write code to do this, okay? It's just some matrix multiplications. So what we're given in this case, we know the extrinsic parameters of the camera, okay? So we know its orientation and position. We also have the intrinsic parameters, okay? And we have this point in 3D space. So the task is to write some code to project the point in 3D space into the image itself. And here's the code, okay? So I formed my rotation matrix, and here is my intrinsic matrix. Here's my translation component, so I'm putting the rotation and translation together. Here's the extrinsic matrix multiplied with the intrinsic matrix. And when I put the intrinsic and the extrinsic matrices together, this is the camera projection matrix, okay? That's denoted by N here. And then I can just take this 3D point, multiply it by the camera matrix, and then dehomogenize. And now I've got the exact location in the image where this 3D point projects to. How cool is that? Okay, so in order for this to work, you need to know all of those parameters, okay? You need to know what the rotation of the camera is. You need to know the focal length and all of that. So in order to get all that stuff, you have to calibrate your camera, okay? So calibration essentially is figuring out what the intrinsic and the extrinsic parameters are for the camera. Now, back when I was a lowly PhD student, I was struggling so much with camera calibration because back then there wasn't a lot of code available, and I had to write a lot of code on my own or get code from other people, and half the time it was buggy, it wasn't working. These days it's great, okay? You've got the MATLAB camera calibration toolbox, which just makes this all super easy. So what you can do is you can use this calibrator app, okay? It's built into MATLAB, and I'm going to show you how it works. So you use this if you have a single camera, okay? So if you have like a webcam, maybe it's on your laptop, or you have your mobile phone, you can use this to calibrate your camera. Alternatively, if you have a stereo rig, okay, here you have 2 cameras, then you can use the stereo camera calibrator app. But here I'm going to talk about just the single camera situation, which I use for a webcam. So if you go to MATLAB, there's this apps button. I'm sure you've seen it. If you go down, there's this camera calibrator app. So this thing's really handy. Okay, so if you want to calibrate a camera, it's not too hard. What you can do is, for example, if you have a webcam, you can grab images from your webcam on your laptop. Now, if MATLAB doesn't recognize your camera, it's okay. There's this thing called the support package installer. You can use that on the MATLAB command prompt, and then you can select USB webcams, and you can log in to MathWorks if needed, and basically install the tools so that you can use your webcam. Okay? Just in case you have a problem with this, if you try it on your own. Okay, so to calibrate a camera, usually what you use is a checkerboard. And this is actually a very special checkerboard because the size of each square is known, okay? So you imagine you can print this thing out, maybe using a printer, and when it comes out, every square is 25 millimeters. So anyways, what you can do is print this thing out, and then this actually defines a coordinate system. Okay, so this is the actual checkerboard pattern that MATLAB gives you. And here's the x-axis going this way, here's the y-axis going this way. Okay, so you can imagine here's the origin. And there's also a z-axis, which is orthogonal to these two axes. Yeah, so if you want to get this thing, you can just type open checkerboard pattern.pdf in MATLAB, and it will open for you. You can print it, and then you're ready to start calibrating your camera. Okay, so here's me in my office trying to calibrate my camera. You can actually collect a whole set of images. For example, you can use 10 or more images. They recommend a minimum of 2 in order to calibrate your camera. And what you do is you just grab a bunch of images, and then once you have those images, it's going to automatically detect all of the corner points. Okay, so you've learned about corner detection earlier. Okay, so here's a great example of using that automatically. And it's also going to find the origin, okay, which in this case is the is this upper left point 0, 0. Okay, and then you can push this green calibrate button in the app, and it will actually calibrate your camera for you. So if you do this, you get all these pop-ups, which all of them are super interesting. So one of these relates to the reprojection error. So essentially what it's doing is finding these points, okay? And they're in 3D space because the 3D coordinate system is defined based on this set of axes, okay? So I know where those points are in 3D space, and I can project them. I can measure how accurate the reprojection is. And typically if you get below a pixel, that's actually pretty good. And here I've calibrated my camera, and the overall mean error is 0.42 pixels. So it's less than a pixel error, which is a really nice result. And here you can actually visualize the error. So ideally, everything would be 0, 0. But of course, there's noise in the measurements, so we get this distribution. You can come and check that out. And it also visualizes the different images, the planes that I use in order to take do the calibration. So here I have a fixed camera, and I was moving this plane in different orientations away from the camera, and here it's all visualized. So it's kind of nifty to look at. And in today's lab, if you choose to do it, there are some images I've given you. In fact, I've given you these images. And you can calibrate my camera using this app, and you can see how it works. Okay, so once you've run this app, it's going to spit out loads of information about your camera. Okay, and in fact, it's got the camera intrinsics and it's got the extrinsics. Okay, so again, for the intrinsics, what you've got is essentially this matrix K. In this case, it gives you the transpose of K. And it's the 3x3 matrix that represents the intrinsic parameters, the things you learned about many lectures ago. So here we've got the focal point, the principal point, the skew. It also gives us the extrinsic parameters. So here are those angles, okay, theta x, theta y, theta z, tells me how the camera's oriented in space. Here's this translation vector, okay, which relates to the camera position in world coordinates. And you can even get the rotation matrix for each of the cameras. Okay, so with all that stuff, okay, you just calibrated your camera, you've got all of those parameters. So you're ready to now form all of these matrices and do this, project points from 3D to 2D. So if you want to, you can write your own code to do this, and here's how you do it. So for each camera, you've got a different translation and rotation component, but the intrinsic parameters don't change, okay? In fact, that's how you can think of the intrinsic parameters relative to the extrinsic. The extrinsic parameters change as you move the camera around in space, but the intrinsic parameters don't. Okay, focal length, principal point, those things don't change when you move the camera. Anyways, so you can put all that stuff, and then here's the camera projection matrix M. And yeah, here's a more compact way to do it. So MATLAB actually has this function called camera matrix. You just pass in the camera parameters that comes out of the calibration app, and then you can give it a rotation and a translation for the current camera. Okay, with me on this? So now we know how to calibrate a camera, and we know how to take 3D points and project them into 2D. Another kind of important concept, though, is lens distortion. So if you have a super expensive lens, it probably has very little distortion, but if you have a cheaper lens, it might have these sort of radial effects. So here we have a pincushion effect, where points further away from the center actually get distorted, and straight lines are actually curved. So this is pincushion because it's a negative radial distortion. If we have a positive radial distortion, it's a barrel effect. It's the same thing, except now instead of these curves being concave, they're convex. Okay? But really what we want is no distortion. Okay? So what we want to do then is, if we have a camera with lens distortion, we want to undistort the image to correct for this behavior. And earlier you learned about the pinhole camera model. The pinhole camera model, it actually doesn't account for lens distortion because it has no lens, right? It's just got a hole where the light goes through. Okay, so if you want to deal with lens distortion, it's not hard. In fact, when you calibrate your camera, it also calibrates the lens distortion coefficients. Typically, it's modeled with two coefficients. We have K1 and K2. And this describes how points move from the center of the image. Okay? So R here is the distance from the center of the image. And if you have radial distortion, then as you move farther away from the center, there's more distortion. So depending on what type of distortion you have, you might be moving further away from the center or closer to the center. But yeah, so you can model this with two radial lens distortion coefficients, and then you, if you have an image that's distorted, in MATLAB you can call undistorted image, and you pass in these camera parameters which have these coefficients built in, and it will undistort your image for you. Okay? So if you look at the image before and after you call this, what you'll see is that there's kind of a warping of the image, especially towards the extremities. Okay, so we've talked about this camera calibration app, and somehow it's magical. I mean, you just feed it a bunch of images, and out pops all this camera calibration parameters. The app itself is quite sophisticated. So, a while ago in computer vision, people were trying to figure out how to calibrate cameras, and it used to be kind of complicated. Now MATLAB has made it so easy. But if you're curious to know more, you can read this tech report. It goes into details about the camera calibration technique that MATLAB is using. And in fact, Zhengzhu Zheng from Microsoft, he was the person who came up with this approach. But essentially, the checkerboard forms a coordinate system. Okay, we looked at that before. And so we have an X and a Y axis, and we know the size of every box, okay? So we know the precise 3D location of everything that's on the checkerboard. So we can detect those corners, okay? So we know where all those points are in 3D space. And what it's doing is it's first solving an equation to find the intrinsic parameters, okay, like the focal length and the principal point. And then it solves another equation for the extrinsic parameters, okay? Now, some of those estimations might be a little incorrect. So what it does is then apply a nonlinear optimization to give you the optimal camera calibration. And again, if you want to know more, it's probably good to check out this description. Okay, so now that we can calibrate the camera, we can do all sorts of cool stuff, including augmented reality. So augmented reality is a really interesting topic, and people have been talking about it for a while. It went through a hype curve, and we thought augmented reality was going to be the next big thing. And it has had good impact in certain areas, but I think a lot of people think that augmented reality still hasn't come to its full fruition yet. But nonetheless, the idea is that you can enhance the view of a real world using computer-generated overlays. So here's an example. Maybe you're outside and you want to take a picture. You can identify mountains, for example, and as you rotate the camera, it's tracking those points, it's projecting them back into the field of view, and everything is smooth and aligned. Maybe you've seen things like this where you're using a smartphone and you can render a 3D view of this motorcycle, making it look like it's actually in the palm of your hand, even though it isn't. So these are some nifty things you can do. And if you have a calibrated camera and you write code to project points from 3D to 2D, then you can do this yourself, okay? So essentially what you want to do is, in this case, I'm loading an image, okay? I've already got my calibrated camera, so I know the translational and rotational components of my extrinsic matrix. And then I've got my intrinsic parameters and this camera parameters. I can form the projection matrix, okay? Once I know that, then I can take points in 3D space and I can project them into 2D, and then I can draw, in this case, lines between those points. And hopefully you can see there's a red cube that's rendered here. So I rendered this cube that's 25 millimeters. It's the same size as the square on the checkerboard pattern. And as I move the checkerboard around that cube, it looks like it's on the paper, even as I'm moving the paper around. So you can take it one step further and project something maybe more interesting, I don't know. So here's a cow, okay? And in MATLAB, you can load up OBJ files. OBJ is a very popular format for 3D surfaces. And then what you can do is just project the OBJ file. So in this case, it's got a bunch of points, but now the points are connected by triangles, okay? So when you render this thing, it's rendering a collection of triangles, and those triangles can even be shaded in MATLAB. So you can see depth. And as I move the paper around, the camera's kind of like, or I'm sorry, the cow is kind of stuck on the paper. So it's kind of a cool effect. So this is how you can do augmented reality by collecting a set of images, calibrating them first, and then augmenting the views. So this works, but the only downside, it's not good for live augmented reality. Because in this case, I'm calibrating each of my views, so I know exactly what the extrinsics are in each of my cameras, each of my views. So I know exactly what the rotation is and the translation. In a live stream, though, you might not know that up front. So what you can do instead is this thing called model-based pose estimation. And here what you're going to do is you're given an image of a known object, okay, like the checkerboard pattern. You know the 3D location of points on the object, and you have corresponding 2D positions in the image, okay? So in my image, I know where the 3D points project to. The idea then is to estimate the extrinsic matrix on the fly. And you can do that. So the goal here is to estimate, the 6 parameters that are in this matrix, okay, given an image of 3D points. So you know where those points are, where they project to, and you also know the points themselves. And you know the intrinsic parameters as well. So the goal is to compute this, given all this stuff. The only downside to trying to compute this matrix is there are nonlinear relationships, especially with all the cosines and things that are in the rotational component of this matrix. So to do this, you need a nonlinear solver. So you can use this thing called LSQ nonlin in MATLAB, and it will allow you to compute these parameters. So in the past, actually, as part of the coursework in this module, we had students do this. Yeah, it was a little heavy when you had to do this on top of all the face detection. So we pulled it out. But nonetheless, if you work on today's lab, you'll get to do some things like this. You won't do model-based pose estimation, but you can project 3D surfaces into a 2D image to do augmented reality. Okay, any questions with that? Okay, here's another example of augmented reality. In fact, this is something I was doing here at City with my PhD student. And the idea here was to do calibration-free augmented reality. And we wanted to use the hand as an input device. So the way this thing worked is the first thing you would do is you put your hand in front of the camera, and it would do an automatic segmentation of your hand. Okay, so you learned about segmentation before. This is pretty much what you learned before. It's a 2-dimensional segmentation. Okay? So you just want to find all the pixels that relate to the hand. And then what we did was, once we had those pixels, they're rendered in red here, then what we wanted to do was find the contour of the hand. And then we, based on the shape of the hand contour, we were then able to infer its position as well as its orientation in 3D space. And if we did that correctly, then we could augment a character into your hand. So, you've got your phone, put your hand out, you can see a character in your hand, and as you rotate your hand, the character rotates along with your hand. And then we're also working on gesture recognition. So as you change your gesture, the character would react accordingly. And our idea was to do like a Dance Dance Revolution with your hand. We didn't get there in the end, but we got some good technology for estimating hand orientation and gesture. So that was good fun. And the way we did that was using machine learning. So we started off using random forest. So I'm sure many of you have heard of random forest. I've heard was talking about that. So what we did was we encoded this contour into a sort of 1-dimensional signal, and then we used random forest to regress the hand orientation. Then later, we moved on to deep learning, where we built a convolutional neural network, which took this image, in this case a 2-dimensional image, and then estimate the orientation. So different ways to solve the same problem, and they had different advantages and disadvantages. Yeah?
Was that just because of the time when it was being done? Like these days, would you still use random forest?
Yeah, that's a good question. Yeah, we found that deep learning worked better than random forest, which I guess isn't super surprising, but we were able to get enough data to make that work. So when we started this project, we had like no data, and we had to, sort of work from small data sets to big data sets. When we started, deep learning probably wouldn't have been a good choice because our data sets were too small. But also at the time, it was right when deep learning was starting to come about, and it wasn't clear if it was better than random forest or not. So yeah, so we chose random forest first, but then when we moved to deep learning, we had bigger data sets, and we were able to get better results. Question in the back.
What was the difference then? You're saying you did this in real time. What was the difference in terms of like speed you used your CNN?
Yeah, so we had to play some, we had to be careful with the image size. So, if you're using like a mobile phone these days, it's like 12 megapixel images, super big. So we wanted to feed in smaller images to do faster inference. But of course, when the images get too small, then it becomes very hard to get an accurate representation of the hand. So we played around with the image size in order to make this practical. So that was sort of how we played that game in order to make it fast. Okay, and here's another example where my student was then playing Mario, actually. So as he closed his hand, he did a jump move, and you can go left and right, and it's kind of a fun way to play a computer game. Okay, so we talked about augmented reality and camera calibration, stereo, depth. Another really interesting question, though, comes when you have more than two cameras. Okay, so we talked about the scenario where you have two cameras, you can find out the polar lines, you can build the geometry of the scene. But what happens when you have multiple views? Okay? So an example could be something like this, okay? Where this is at Carnegie Mellon University in the USA. These researchers built this hemispheric dome, and they've mounted over 50 cameras in this environment. And then a person went into there and did some sort of action, and then they wanted to record that action in 3D. You can imagine other scenarios where you have just a static scene, but you're going to use a single camera that gets moved around, so you're going to have a video sequence. So what can you do in an environment like that where you have more than two views? Well, a very important problem in computer vision is structure for motion. You might also hear the term SLAM that's often used in this context. The idea is that you have two or more images, and what you want to do is compute the position of the points in 3D, okay? But not only that, you also want to compute the camera projection matrices. So you want to know both the intrinsic and the extrinsic parameters. So you can imagine this is quite a difficult optimization problem because you want the structure, which is the three-dimensional points, and the motion, which relates to the extrinsic and intrinsic parameters as well. And in this environment, usually what you're doing is you have a video camera and you're just moving it around a static scene. That's the typical scenario. So the pipeline looks like this. You've got a video that's coming in, and the first thing you have to do is track points. So you need to find some good points, like surf, for example. Then you're going to track those points through the video sequence. And based on the correspondences you find through tracking, you can then do a 3D estimation. So that gives you the structure, where those points are in 3D. And you can also do some optimization to figure out where the cameras are and refine the 3D positions. So what pops out of here are the 3D points and the projection matrices for the cameras. Okay, so in order to do structure for motion, what you're given are a collection of images, and in this case I'm calling them n images, and I have n points that are in 3D, and those points aren't moving. Okay, the camera's moving, but the points aren't. So here I've got these points, they're rendered in red, they're in 3D, okay? And they're going to project to these points Q in these different views. And the projection is based on the camera projection matrix. We just described that earlier in this lecture. Okay, so what you have are these points in the images, and you track those points from image to image. And the goal is to estimate the points in 3D and the camera projection matrices. So given Q, give me big P and big M. Okay, so we're going to start off. We're going to first find some points to track. And in fact, we're going to cover tracking next week, so stay tuned for that. But there's some good ways to do that. And in fact, the KLT tracker is a great option. And I'll describe that in detail next week. But essentially what you're going to do is you're going to find some points, like some surf points. You're going to track them using the tracker. And you also want to be able to deal with points that come into the field of view or exit the field of view. So you've got to be able to handle that because as the field of view changes, some points might leave, some other points might come in. Okay, so once you track those points, then what you want to do is estimate 3D where those points are. So So what you do first is you compute the fundamental matrix between two of the views, and I described earlier how you might do that. So then what you can do is set your first camera matrix to the identity matrix, and use this camera pose function to compute the relative rotation and translation to the next camera, given the points that you've tracked. Okay? And once you've done that, then you've got a camera projection matrix for the second view. So now you know how to project points from 3D to the first view, and the same thing for the second view. Okay? And the thing that makes that work is the fundamental matrix. Once you can do that, then you can actually triangulate back into 3D and get the 3D position of those points. Okay? So here's kind of a scenario where I've got a point in this image, calling it P1, and I have a point in this image, P2. If I know the camera projection matrix, actually what I can do is I can back project into 3D space. So if I have this point, I can back project into 3D along this line. And I can do the same thing over here. And the point that is where these lines connect, that's my point in 3D. Okay, so that's triangulation. The reality is that these lines might not actually cross, but you can find the point that is optimally close to the two lines. So anyways, to do that, it's not super hard, but what you typically do is set up a system of linear equations. Okay, that's kind of what we do in this module. And what you're going to do is solve for the point in 3D. So essentially, here's the point in 3D. Okay, here's my camera projection matrix, and here I'm projecting it into 2D. Okay, so this is exactly what we did on the board just a few minutes ago. So you can write that out, and you can have that for your two different views. And then what you can do, since your camera projection matrix is known, so these M vectors, these encode the different elements of the M matrix. This is all known. The goal is to compute P in 3D, where everything else is known. And so if you have two or more images, you can solve for this. And in fact, in MATLAB, there's this function called triangulate. So essentially what you do is you give it these matched points and these two camera projection matrices. The points are in 2D, and it will tell you where that point is in 3D. Okay? So essentially what we've got now is a way to estimate the camera projection matrices, and now we've got a way to get the point in 3D space. And yeah, you can solve this using linear equations as long as you have two matching points. So you need at least two images. Are you with me? Okay, so once you can triangulate, you've got an initial estimate of the points in 3D space, so you know P. We now know M. Okay, so we've actually kind of solved the problem already. I started off with these points Q, and then I was able to compute the projection matrices, and then I was able to get the points in 3D. The last step is just to do an optimization to kind of fine-tune the estimation to make sure it's really good. And that's sometimes called bundle adjustment. Okay, so anyways, that's how it works. And in MATLAB, you can actually program all this stuff, okay? And it's not super hard. The code is maybe a little more involved than some of the other examples we've looked at. But here, for example, is a two-view case where I have these two views, a left and a right view, okay? And what I'm going to do is I'm first going to undistort the image. Okay, so we talked about radial lens distortion. This is actually undistorting the image. And actually, you can kind of see it here. So here's the original image. Here's the undistorted image. So there's kind of a little warping of the image towards the center. And now straight lines in this image should actually appear straight. Okay, then what we're going to do is we're going to find some good features to track. These could be surf points, but in this case, they're called min eigenfeatures. I'm going to describe those next week as well, so stay tuned. But essentially, we've got these points, and we're going to track them into the next frame. And then what we're doing is showing the points that were tracked, and they're matching. Okay. So it's just a point, just a way to track the points in 2D. And then here's where it gets interesting. So we're going to estimate the fundamental matrix, okay? And in this case, it's using this MSAC technique. It's kind of like RANSAC. And here I'm actually configuring the number of trials I'm going to do. So how many points am I going to sample and then try to estimate my matrix. Here I've got my inlier points, I'm visualizing them, and then I'm estimating the camera pose. And then I can triangulate into 3D to get these points in 3D. And then now I'm pretty much done. So I know where the points are in 3D, I know where the cameras are, and I can project from 3D to 2D. And here what's happening is it's visualizing the reconstructed points as a point cloud, okay? And I'm also visualizing the camera location using this plot camera function. And if you look here, what I've got are the points that were tracked by the tracker, okay? And I've got an estimate of where the cameras are relative to the points. And I've got the points themselves, and everything's in 3D now. So that's the really cool thing about structure for motion. Just from a video sequence, you can infer all of this 3D stuff. You can infer where the points are that have been tracked. You can infer where the cameras are and how they're related to each other. Okay, I'm running out of time, but if you get a chance, please check out the slides. If you click on this link, it's going to show you a really cool structure for motion application where they went onto Flickr and they took like thousands and thousands of images of popular locations. And then they used structure for motion to estimate where all the cameras were, and then to fuse all of those images together to create a 3D representation from a huge collection of Flickr images. And you see like a large world environment, it's like a city. And they were able to do that using structure for motion. So super cool application. Please check it out. Okay, before I wrap up, I just want to talk about one more thing, which is RGB. So far in this class, you've been learning about RGB images. But recently, there's been some new devices that have come out, like the Kinect, for example, that measure depth from the camera. Okay, so instead of doing it with stereo, these techniques usually use infrared. And they're able to produce a depth map, infrared or time of flight, which will estimate the depth from the camera for every pixel in the view. And if you do that, you get something like this. So here's my RGB image, and here's my depth image. Here, an image, a pixel that's brighter is closer to the camera than a pixel that's farther away. And these days, there are loads of these RGBD data sets available, and you can use them to solve different computer vision problems. And in MATLAB, you can actually do point cloud processing. So here you can load a point cloud, you can write a point cloud, you can actually fit shapes to point clouds. So here, for example, this is the globe that we reconstructed using structure for motion. All of these points are on a sphere, okay? And you can use like these functions like PC fit sphere, which will actually try to fit the sphere to the data. And you might not be surprised to learn that this function uses RANSAC in order to fit a sphere to a noisy collection of points with a bunch of outliers. So anyways, you can play around with that. That's all in MATLAB as well. Okay, I think I'm out of time. So any questions? Okay, so why don't we wrap up there? We've got the lab tonight. You're welcome to do Lab 8. It's on Moodle, but I think many of you are also super interested in coursework, so feel free to work on that. Slabaugh is here, and if you want to hear, I can try to help.